Hi, this video presents a quick review of the feed fasting cycle. We'll begin by looking at a graph at how we maintain our blood glucose levels with time. So this graph is for an adult. Timescales for children, especially very young children and infants, are quite a bit shorter than this. So in this graph, time 0 is having consumed the last meal, and assuming that the meal has some carbohydrates in it, we first maintain our blood glucose from the carbohydrates that were in that meal, the exogenous carbohydrates. So blood glucose levels rise, that causes an increase in blood insulin, and we utilize that blood glucose typically within about 3 to 4 hours. Usually within a couple hours after the meal, blood glucose levels drop again to below about 100 milligrams per deciliter, and insulin levels drop down closer to their basal level in the blood, and liver glycogen is activated to be broken down to release glucose into the blood to maintain our blood glucose level. So during the time period between meals, it's mostly liver glycogen that maintains our blood glucose. If we don't eat again for another 4 hours to, say, overnight, then the processes of gluconeogenesis, so synthesizing glucose by the liver as well as by the kidney cortex from non-carbohydrate precursors like glycerol and lactate and amino acids, gluconeogenesis becomes activated, as well as lipolysis, so releasing fatty acids from adipose stores. And most tissues in the body switch over to oxidizing fatty acids, sparing the glucose for utilization by the brain, by red blood cells, etc. And note that by about a day of fasting, 24 hours, there is essentially no glycogen left in the liver, so we become totally dependent on gluconeogenesis to supply blood glucose. If the fast continues for 1 to 2 days, then the process of ketogenesis, or the synthesis of ketone bodies in the liver, is activated. These ketone bodies are made from acetyl-CoA, which comes from fatty acid oxidation occurring in the liver. And these ketones are a way to supply energy, particularly to the brain, but also to heart, to muscle, to kidney, etc. And this helps spare the glucose so that gluconeogenesis levels actually begin to drop and are maintained at a constant lower level throughout the length of the fast. This helps spare muscle protein, since muscle protein is one of the main suppliers of the substrates for gluconeogenesis. Now we'll review what's happening in several important metabolic tissues during the feed fasting cycle. So after a carbohydrate-containing meal, blood glucose initially rises, causing an increase in insulin signaling from pancreatic beta cells. The high levels of glucose in the portal blood cause the liver to take up lots of glucose and utilize much of it for glycolysis to meet its own energy demands. Insulin signaling also stimulates glycogen synthesis in the liver. The elevated insulin signaling inhibits gluconeogenesis. This results in a decrease in glucose release from the liver. Recall that in patients with diabetes that lack sufficient insulin signaling, the liver continues to release glucose even when there's plenty of glucose in the blood. Fatty acid oxidation is inhibited by the glucose availability and the high levels of insulin signaling. Fatty acid synthesis can also be activated in the liver under these conditions. In skeletal and cardiac muscle, insulin signaling causes the GLUT4 glucose transporter to move to the plasma membrane, allowing lots of glucose to enter the cells. That glucose is used both in glycolysis and glycogen synthesis. Again, fatty acid oxidation is inhibited under these conditions. The increased insulin secretion also inhibits muscle protein breakdown or proteolysis, while at the same time increasing the amount of protein synthesis or protein translation. This results in a decrease in the amount of amino acids released from muscles. The lipoprotein lipase in the capillaries of adipose tissue is also activated by insulin. This results in increased fatty acid uptake. Insulin signaling also promotes the movement of GLUT4 to the plasma membrane, allowing more glucose into adipocytes. Glycolysis increases, and this provides the glycerol 3-phosphate required to build triacylglycerols. Triacylglycerol synthesis is activated. At the same time, the lipases within adipocytes are inhibited strongly by insulin. This includes hormone-sensitive lipase. So there's a decrease in lipolysis and a decrease in the release of fatty acids from adipocytes. Together, this presents a picture of insulin stimulating growth and building of storage molecules throughout the body. Several hours after a meal, after most of the nutrients have been absorbed from the intestines, it's called the post-absorptive state, blood glucose levels return to their normal level, somewhere usually between 80 and 100 mg per deciliter. Insulin levels drop down to their normal basal level, and glucagon starts to be released from the pancreatic alpha cells. This increases the breakdown of glycogen in the liver, decreases the synthesis of glycogen, starts to begin to activate gluconeogenesis, although there's not a whole lot of de novo glucose synthesis occurring yet, and glycolysis is inhibited under these conditions. This allows the liver to begin releasing glucose to maintain blood glucose in the body. The liver makes most of its ATP now by oxidizing fatty acids. In muscle, GLUT4 is re-internalized into the cells and glycolysis decreases. Of course, this depends on the muscles being at rest. If the muscles are exercising under these conditions, then GLUT4 levels stay elevated and glycolysis will continue. However, glycogen synthesis is decreased in this state of lower insulin signaling. And just like in the liver, fatty acid oxidation is increased in the muscle. So the muscle again makes most of its ATP now from oxidizing fatty acids. And with the lower insulin signaling, proteolysis begins to rise and protein synthesis begins to drop. In adipose tissue, lipoprotein lipase activity drops and fatty acid uptake decreases with this lower insulin signaling. GLUT4 transporters are re-internalized into the adipocytes and glycolysis decreases. Triacylglycerol synthesis is inhibited, while now lipolysis is activated. So hormone-sensitive lipase and the other lipases within adipocytes are activated to begin releasing free fatty acids into the blood. And it's this increase in free fatty acids in the blood that allows muscle, liver, and many other tissues to increase their amount of fatty acid oxidation. Now we've entered the period of fasting. And the main differences that you'll see is that glycogen breakdown is decreasing because there's just not as much glycogen left in the liver, and gluconeogenesis is really taken over to maintain blood glucose levels. The liver and all the other tissues are oxidizing lots of fatty acids, and the liver is starting to make more ketones. Okay. Also, there is an increase in amino acids being released from muscle. Those amino acids are largely being used for gluconeogenesis. The increased fatty acid release from adipose is very important at this stage. During long-term fasting or starvation, the main differences are a large increase in the amount of ketone body production by the liver and a bit of a decrease in the amount of glucose released. This helps spare the amino acids being released from muscle. And muscles and many other tissues are using the ketones. Liver does not use ketones itself, but most other cells in the body can, including brain. And the adipose is still releasing fatty acids as well as glycerol. That is still an important substrate for gluconeogenesis. So here we are back to our original graph. I hope it's now clear how during the process of the feed fasting cycle, we both maintain blood glucose and what types of macronutrients supply energy during different phases of this feed and fasting cycle.